Ilalaban kahit kanino, oo, simple lang ako at malabo mong magtipuhan. Kaya okay nang kahit sa FB mo lang mapusuan. Kasi di na mapigilan ng sariling mapaibig sa iyo. Ano ba to? Gusto ka laging na...
Okay, now let's go to the nature of chemical bonds. So, why do atoms bond together and how can bonds be described electrochemically? Okay, so basically, atoms bond together because they want to become stable. Okay, so how does this bond or how does these atoms become stable? Okay, so when they bond together, they release energy. Okay? So that means if they release energy that is exothermic, they become more stable than its starting material or than its atom itself. Okay? So it bonds to another atom because it enables them to become more stable than being themselves. Okay, so than being them alone. Okay, so that's why they want to bond with another atom because they want to become more stable. And after they combine to each other, they already have these bonds. They actually release energy, and when they release that energy, that that act or that compound that is formed after that bond is actually lower in energy. So that means it's lower in energy, it becomes more stable. Okay, so that is the concept of that. So to fully understand what I meant, okay, I have here the representation for that. So for example, if you have two carbon and six hydrogen, so when these two carbons and six hydrogens so link together or to form a bond, so they actually form ethane. Okay, so this ethane is actually more stable than being alone or being two carbons only and six hydrogens. Okay, so two carbons and six hydrogens is not stable because they tend to find another atom so that they will bond to that another atom and they will be stable or their structure will be stabilized. Okay, so this ethane molecule is now more stable than the starting material. Okay, and when these two carbons will bond with six hydrogen, it actually releases energy. Okay, and since energy is released, so that means the overall energy for ethane is lower, and therefore is it lower in energy, then this becomes more stable. Okay, but to understand fully what I meant by this, so I already discussed that a lower energy will have a more stable structure. Okay, so and this energy that is actually released will be will be the one if we want to break the bonds of that formed compound. That energy release would be supplied to that formed uh, compound in order to break the bonds. Okay, so that's it. Okay, to fully understand what I meant, so for example, okay, so we knew that atoms are actually has its own valence shell or valence electron. Okay, so when we say valence electron, it's only a review. A valence electron is the outermost electron in the orbital. Am I right? So looking at your periodic table, you will know the valence electron of each atom. So for example, for group 1 element, the valence electron is 1. Okay, for group 2, the valence electron is 2. For halogens, the valence electron is 7. Okay, for oxygen, the valence electron is 6. Okay, for nitrogen, that is group 15 or 5A, the valence electron is 5. For carbon, the valence electron is 4. That is for carbon group. For boron group, the valence electron is 3. Okay? So to attain a stable configuration or a stable valence shell, okay, so we look at first what are those atoms that are actually stable. Okay, what are those atoms? These are actually the noble gases. So noble gases are stable on its valence shell. Why? Because they have already a total of 8 electrons on its valence shell. Or the outermost electrons is, the total is already 8. So this is what we call the 8 electron rule. Okay, so atoms that don't have 8 electrons on their valence shell will tend to will tend to share its electrons, or to give its electrons, or to accept electrons, so that their valence electrons would have a total of 8 electrons, and that will obey the octet rule, and they will become more stable, or they will become stable because they have already the same configuration, the same number of electrons on its outermost electrons or in its valence shell with the noble gases. Okay, so the noble gases are stable because they have already an 8 electrons on its valence shell. So those atoms that have no total of 8 electrons will eventually bond to another atom so that they will attain a more stable valence shell. And that's what we call the octet rule, or the 8 electron rule. Okay? So like for example, ionic bonds. But when we say ionic bonds, it's the bond between a metal and a non-metal. So metal will eventually loses its electron, while the non-metal will accept the electron. So for example of metals, like for example potassium, which belongs to the group 1 element. Okay, so potassium will lose its electron, or one electron, so that it becomes same electronic configuration with argon. Okay, so potassium is 19, so it has 19 electrons, and argon has 18 electrons. So potassium will give up its one electron, so that it becomes the same electronic configuration with argon. Okay, so they are already the same configuration, they have already the same 8 electrons on its valence shell, so therefore potassium is more stable now if it gives off its one electron. Okay, so and example again for that's potassium. Okay, so for calcium, for example, calcium, it has 20 electrons, a total of 20 electrons. It belongs to the group 2. So what do you expect with calcium? So calcium, to be able to attain the same electronic configuration with the argon 18, so calcium will give off its 2 electrons. Okay, that's right, 2 electrons. In order for calcium to be more stable than calcium itself. Okay, so calcium will lose its uh, 2 electrons in order to become the same electronic configuration with argon. Okay, now let's go to the non-metals. So for example, we have oxygen. Okay, oxygen has a total valence electron of 6. Okay, so what do you expect with oxygen? Is it will give off its electron, or it will accept electrons? That's right. It will accept electrons because it only has 6 electrons on its valence. Okay? So the tendency for oxygen is that it will accept 2 electrons, so that it would have a total of 8 electrons. Okay? So that becomes oxygen the more stable, and will follow the octet rule. Okay, so it will accept 2 electrons, and therefore it will become more likely like a neon, which has a 10 electrons, right? So oxygen has 8 electrons, 8 electrons, okay, but the valence is different, huh? So the valence has 6 electrons, okay, so it will accept 2 electrons, and it becomes, it will follow now the octet rule, okay, or the 8 electron rule. Okay, so ionic bonds are actually giving off, the metal will give off its electron, while the electrons that the metals are given off would be accepted by the non-metals. Okay, so ionic bonds, basically it's a bond between your metal and the non-metals. Okay, well, covalent bondings, it's actually there's no giving off of or accepting of electrons. There's no giving of electrons, but rather all electrons are shared by the atoms. Okay, that is the difference between ionic and covalent. Okay, for ionic bonds, there is a giving off and accepting of electrons, or it's a bond between your metal and the non-metal. While for covalent bonding, the electrons are being shared. Okay, so basically covalent bonds, we can say that these are actually bonds uh, between non-metals, because mostly non-metals, they will not give off its electrons, but rather they will only share their electrons. Okay, so we can represent covalent bonding. So we will focus more on covalent bondings, because basically organic compounds will be more on the covalent bonds than in ionic bonds. Okay, so we can represent covalent bondings by its Lewis structures or the Kikuli structure, or Lewis structures first. Okay, Lewis structures or the electron dot structure, and the other one is the Kikuli structures or the lined bond structures. Okay, remember that what did Kikuli propose? That in the two-dimensional structure of the organic substance. So that is actually the lined bond structures. Okay, the Lewis structure is more on the electron dot structure, while the Kikuli structure is more on the line bond structure. So to really understand what I meant with this, so next slide is shows what is the Lewis structure and the line band structure. Okay, remember electron dot structure. So carbon has a 4 valence electron. Okay, carbon has a 4 valence electron. Hydrogen belongs to the group 1 element, so it could have only 1 valence electron. So valence electron is very important, because the valence electrons will be the one to bond, to form a bond. Huh? It's very important that you will know the valence electrons for each atoms in the element, or in the periodic table. Okay, so carbon belongs to the group 4, so, and it is a tetravalent carbon, so therefore it has a 4 valence electron. Hydrogen is group 1, so it has only 1 valence electron. So to represent the electron dot structures or the Lewis structures, okay, you will just spread the electrons for carbon, that is total of 4, and you connect the electron for hydrogen, which is only 1 valence electron. So remember that it should be electron pair. Huh? It should be electron pair. So how many total electrons are already here? We have 2, 4, 6, 8. So there are already 8 electrons. Then it follows the octet rule. Okay, so already follows the octet rule. Then this is now a stable compound. Okay, it has a lower in energy. So that means carbon can bind to 4 hydrogens, because it follows the octet rule. So how about your nitrogen? So nitrogen belongs to the group 5 element. Okay? So group 5 contains 5 valence electrons. So you have 1, 1, 2, 3, 4, 5. Okay? However, the one of its electrons are actually paired already. Okay? So there are only there is already a 2 electron pair for nitrogen. So the remaining electrons are actually, there is no pair. Okay, so 1, 2, 3. So we already knew how to to draw the electron dot structures for an atom, di ba? We already knew that. So we should actually write it like, so for example, nitrogen, so it should be spread. It should be written in, to spread the electrons like 1, 2, 3, 4, then, or we'll start here. So 1, 2, 3, 4, and 5. So that means that one of each side for this symbol has an electron pair, and the remaining three sides have no electron pair. So that means that nitrogen can be able to bond with hydrogen, only 3 hydrogen, because of these sides has no electron pair yet. And to complete the octet, that is 5 electrons plus 3 electrons coming from the 3 hydrogens, and a total of 8 electrons. So 5 plus 3, that becomes 8 electrons. In the case of oxygen, it's already have its 6 electrons. Okay, so when you write the electron dot structure for oxygen, you will notice that 2 of its sides have already electron pairs, and the 2 sides have no electron pair. So that means if it will bind to the hydrogen, then therefore there are only 2 hydrogens that will bind to oxygen, giving this a total of 8 electrons. Okay, so this is now the electron dot structure for water. So that's it. Okay, so for the line band structures, we can also, instead of its electrons, we can represent a line. Okay, your C can bond with your hydrogen. So each of these bond contains how many electrons? 2 electrons. So each bond contains 2 electrons. So 1, 2, 3, 4. There are 4 bonds and a total of 8 electrons. Okay, so we can represent, so this electron pair here now becomes what we call the lone pair. Okay, lone pair. Okay, so this is for the water, that is for ammonia, this is for methane, for ammonia, for water, and for methanol. Okay, so remember, they have only 8 electrons for carbon already. You have also 8 electrons for oxygen. Okay, so that is how do we write the electron dot structure and the line band structure. Okay, okay, so we have here a question regarding what we have learned about chemical bonding theory and also the nature of chemical bonds. So these are the questions. So for example, how many atoms does phosphorus bond to in forming phosphine? So the formula for phosphine is P, phosphorus, and a hydrogen. But we don't know how many hydrogens are there. Okay, so how do we do that? Okay, remember your phosphorus. Remember that in forming chemical bonds, what are the electrons involved? Valence electron. That's correct. It's valence electron. Okay, so we should know what is the valence electron for phosphorus and what is the valence electron for hydrogen. So looking at your periodic table, your phosphorus belongs to the group 5A elements. At the top of phosphorus is nitrogen. And we already knew that nitrogen contains 5 electrons. So how do we draw the electron dot structure for phosphorus? So we have 1, 2, we have 3, 4, and 5. Okay, so a total of 5 electrons for phosphorus. Now for hydrogen, how many valence electron are there in, or is there in hydrogen? Only 1 valence electron. That's correct. So if hydrogen has only 1 valence electron, and phosphorus has already 5 electrons. So how many hydrogens are needed to complete the octet? Okay, there are 3 hydrogens needed. That's correct because hydrogen has only one valence electrons. So in order for phosphorus to complete its octet or 8 electron rule, we need to have 3 hydrogens so that the electron for hydrogen here would be there, and also here we have also another hydrogen to complete the octet here, and another hydrogen to complete this electron pair. So how many electrons are already there? 1, 2, 3, 4. There are 4 electron pairs and a total of 8 electrons, and this will suffice or satisfy your electron rule or the octet rule. So therefore the formula for phosphine would be P, H, H, and 3. That's correct. Okay? So next is draw the electron dot and the line structure of chloroform. Okay? So chloroform. I will erase this first. Draw the electron dot and line bond structure of chloroform. Okay? Chloroform contains 1 hydrogen and 3 Cl. Okay? Remember that your carbon is actually the central atom, diba? Okay, that would be the central atom for now. Okay, so what are the electrons involved in bonding? Okay, what is that? The valence electron. So we should know first the valence electron for carbon, for hydrogen, and for chlorine. Okay, for carbon, how many valence electron? There are actually 4 valence electron. For hydrogen, there is only 1 valence electron. And for chlorine, this belongs to the halogen groups, which contains 7 valence electron. Okay? So how do we do this? How do we draw the electron dot and the line band structure for chloroform? Okay? So carbon becomes our central atom. Okay? Remember that your carbon has 4 valence electrons, so we will spread out the electrons. Okay, 1, 2, 3, and 4. Okay. So hydrogen has 1 electron, so we can put the hydrogens here. So we can put the hydrogens there. Okay. Chlorine has a 7 electron. So how do we draw the electron dot structure for chlorine? Okay, so 1, 2, 3, 4, and you have 5, 6, and 7. So in this case, we have only 3 electron pairs already. So this will not be involved in the bonding. And this 1 electron here would be the one to bond with, or will be the one to be paired with the electron in the carbon. Okay, so we can write now chlorine here. Okay, we can now write chlorine there. So this electron of chlorine is this one. Okay, then the remaining electron pair, which is actually 6 electron pair. Okay, 6 electron pair, 6 electron pair, and so forth. So we can write there are actually 3 chlorines. Am I right? So there are 3 chlorines. So we can also write there dot 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 dot, okay, dot, and there's no space already, but you just visualize it that there is 2 electrons, okay, below the Cl. Okay, and also we have also Cl here. So electron of that Cl. Okay, 2 electrons, 2 electrons, 2 electrons, 2 electrons. Okay, so this is now the representation for the electron dot structure for Cl. How about the line bond structure? Okay, So I will erase this first. So remember that each bond contains 2 electrons. That's right. Okay. So to represent the line band structure or the Kikuli structure, so you have carbon. So remember, this is 2 electrons, so we can represent this as 1 bond, and that is for hydrogen. Okay. This is 2 electrons. We can represent that also for chlorine. And don't forget the lone pairs, okay? The lone pairs for chlorine. And also we can represent the other side for chlorine. And the lone pairs are 3 lone pairs. So this is very important that you will write the lone pairs, okay? You will know later on that it's very important, okay? So this is now the line band structure for chloroform. Then you're done.